Okay, let's go ahead and get started. Now that we have a little bit better appreciation for the physical and chemical characteristics of acids and bases, we want to shift our attention to the qualitative aspects of acid-base chemistry. In other words, we want to know the mathematics of acids and bases. Well, where do we start? I think a good place to begin is with this flask of distilled deionized water. And you may ask, why start with water, which we generally associate as being neither acidic or basic. In fact, water is both acidic and basic, and we'll talk about that a little bit later. But the important thing is that water is really the staging area for all acid-base chemistry. When we say, for example, that something happens in an aqueous solution, what we really mean is dissolved in water. So if we understand what's happening in this flask, we're going to have a much better chance of understanding acid-base chemistry. So let's start there. If I were to ask you to magnify your vision thousands of times and look into this flask and tell me what you saw, most of you would tell me that you see water molecules banging into each other, banging into the size of the vessel that it's in, and you'd be at least partially correct. So that's a very, very good start, H2O molecules. But that's not all that's in that container, because water is in a state of what we call dynamic equilibrium. And dynamic equilibrium really means that water is in a state of constant flux. In other words, water molecules, like the one that we've just described, are constantly dissociating, or what we call ionizing. So I'm going to make an arrow like that to indicate that water ionizes. It forms H plus and OH minus ions. But just as rapidly as H plus and OH minus ions are generated, they come together again to reform water, and that's the nature of this equilibrium, the dynamic equilibrium that occurs between water and its component ions. But the story doesn't end there. H plus ions also reassociate in some cases with the water molecules that are already there to form hydronium ions, H3O plus ions, and so there's a second type of equilibrium going on in this direction, just like that. Now, for our purposes, H plus and H3O plus are going to have the same concentration. So you'll often hear me say hydrogen ion concentration and then write H3O plus concentration, or vice versa. It's commonly done, and that's perfectly okay. Just understand that H plus and H3O plus are not exactly the same thing, but they do have the same concentration, and so we'll use them interchangeably. So we see this overall equilibrium. Well, an equilibrium implies an equilibrium constant, and certainly we have an equilibrium constant in this case, and we call that equilibrium constant Kw. It's a very important number for us because it's going to help us to understand the relationship between hydrogen ions and hydroxide ions. As it turns out, the product of hydrogen ions and hydroxide ion concentration, the product of those two concentrations, is equal to Kw. And we know what that number is. It's 1.00 times 10 to the negative 14. 1.00 times 10 to the negative 14 is always the product between H plus and OH minus. Now, why is that important? Well, it's important because from this point forward, if we know the hydrogen ion concentration, we know that, or can figure out, the hydroxide ion concentration, and vice versa with a little bit of algebra. Now, let's talk a little bit more about this water. Water, we know, has a neutral pH. It has a pH of 7. That means that the concentration of hydrogen ions in this water and hydroxide ions in this water is essentially the same. It's almost nearly the same. Now, if the product of those concentrations is equal to 1 times 10 to the negative 14, that means that each one of those concentrations must be the same. And those concentrations are 1 times 10 to the minus 7 for hydrogen ion concentration and 1 times 10 to the minus 7 for hydroxide ion concentration. But remember, that's only for pure distilled deionized water. If one of these or the other begins to predominate, then the solution becomes acidic or basic. For example, if we have an accumulation of hydrogen ions, more hydrogen ions than hydroxide ions, the solution begins to become acidic and the pH is driven down. If the hydroxide ion concentration begins to predominate over the hydrogen ion concentration, then the pH is driven up towards 14. So we use this relationship then between hydrogen ions and hydroxide ions to be able to begin to make preliminary calculations in acids and bases. And so let's start there. Let's take a look at a problem. Our first problem says this. It says a solution has a hydronium ion concentration. Remember, I could have just as easily said hydrogen ion concentration. They're the same for our purposes. But a solution has a hydronium ion concentration of 1 times 10 to the negative 8. And we want to know what the hydroxide ion concentration is. Well, I can put my pen down. I don't need a calculator for this problem because of the fact that I know a little bit about exponents, and you should too. From your algebra class, you should know that exponents, when you're multiplying numbers that have exponents, as long as this base is the same, all I have to do is add those exponents together. So I now know that the product of the hydronium ion concentration and the hydroxide ion concentration is 1 times 10 to the negative 14. So to answer this question, all I need to do is figure out what the number is that adds to negative 8 to give me negative 14. And of course that number is negative 6. So without using a calculator and without doing any calculation on paper, I can figure out that the hydroxide ion concentration, by the way we use brackets for concentration, is equal to 1 times 10 to the negative 6, and I'm done. Okay, it's that simple, it's that easy. All right, let's go on to the next problem. Number 2 says a solution has a hydroxide concentration of 3.34 times 10 to the negative 5. 3.34 times 10 to the negative 5 is my hydroxide ion concentration. The question is, what is the hydrogen ion concentration? What's the hydrogen ion concentration? Well, we've already said that once we know that Kw, once we know that the relationship between hydrogen ion concentration and hydroxide ion concentration is 1.00 times 10 to the negative 14. If you give me one, I'll be able to figure out the other one. Now this is not going to be as simple as problem number 1 because of the fact that the base is not 3.34, so I'll need to use a calculator, but it's really not a problem. I'll show you how to do that on this calculator here. I'm going to be using a TI-30X. This is the calculator we're going to be using predominantly in the classroom, but if you're using a different calculator, make sure you can punch the buttons in correctly to get to the right answer. All right, so here we go. We know the hydroxide ion concentration. We're trying to get at the hydrogen ion concentration. So we want to isolate hydrogen ion by itself. So to do that, I'm going to divide both sides by the hydroxide ion concentration, and I get H plus is equal to 1.00 times 10 to the negative 14 divided by the hydroxide ion concentration, which I now know is 3.34. 3.34 times 10 to the negative 5. And now it's just a matter of a little calculation on this calculator, and here's how it's done. What I'm going to do is begin by turning the device on. Just hit the on button in the lower left hand corner, and I'm going to hit 1.00, and then watch this. I want to account for this exponent, the negative 14. Now the way that I do that is to use the EE button. It's the simplest way that I know of to get to exponents into the number. Second EE, and then negative 14, and I've got 1.00, it has a capital E there, negative 14, and then divide that by 3.34, again, second EE, negative 5, and hit the equal button. And what I get is 2.994 times 10 to the negative 10, but I have 3 significant digits here, 3 significant digits here. The lesser of those two is 3 significant digits. I'm just going to take the less of those two, and it is 2.99 times 10 to the negative 10. So the hydrogen ion concentration then is 2.99 times 10 to the negative 10. And I'm done with problem number 2. All right. So we have a good idea then of how to go from hydrogen ion concentration to hydroxide ion concentration and vice versa. So we're going to introduce now our second set of equations, and these were introduced in the early 1800s by an individual whose name was Sorensen, who gave us the logarithmic scale. And what Sorensen said was, look, let's not deal with these numbers like 1 times 10 to the negative 10 or 2.99 times 10 to the negative 10 or whatever the case may be. He devises a scale that goes from 1 to 14, with 1 being the most acidic and 14 being most basic, and 7 right in the middle. And what he did was convert concentrations into what he called pH. Here are the formulas. pH is equal to minus the log, that's log, that's base 10, not base E, but base 10, the log of the hydrogen ion concentration. So pH is equal to minus the log of the hydrogen ion concentration. pOH is equal to minus the log of the OH minus concentration. And one final formula, and that is that pH plus pOH is equal to 14. So if I know the hydrogen ion concentration, I can easily find the pH. If I know the hydroxide ion concentration, pOH is a breeze. And if I know either pH or pH or pOH, finding the other one is no problem whatsoever because of the sum of those two is 14. So let's use those equations now to solve problems. Let's take a look at problem number 3. Here's what it says. It says the hydrogen ion concentration of a solution is 1 times 10 to the negative 4. What is the pH of the solution? So the hydrogen ion concentration is 1 times 10 to the minus 4. What's the pH of this solution? Well, all I have to do is use the pH formula, and here's what it says. It says pH is equal to minus the logarithm of the hydrogen ion concentration. Remember, I could have placed hydronium ion concentration there. It's the same thing. So pH is equal to then minus the logarithm, and I'll just plug in the 1 times 10 to the negative 4. 1 times 10 to the negative 4, just like that. And so I'll put that into the calculator, and here we go. I'll clear the calculator first. So pH then is equal to minus log. Be careful, don't hit ln, that's for natural log. Log minus the log of 1 second EE negative 4, close the parentheses, and when I do that, I get the number 4. So the pH is 4. Now, I want to show you a little trick. You could have easily gotten this answer without the use of a calculator if you just remember one thing. Log and power and exponent all mean the same thing. They all mean the same thing. So, if I'm told that the hydrogen ion concentration is 1 times 10 to the minus 4, and I want to know the pH, just take the negative power. In this case, the negative of a negative 4 is positive 4. So the pH then is 4. All right, now that only works, you can only use that shortcut if this first number here is a 1. So if this had been 1 times 10 to the minus 9, the pH would have been 9. If this had been 1 times 10 to the minus 3, the pH would have been 3. If this would have been 1 times 10 to the minus 7, the pH would have been 7, and that would have been a neutral solution. But it's 1 times 10 to the minus 4, so I can surmise then without a calculator that the pH is 4. That the pH is 4. Okay? All right. That makes this an acidic solution, by the way. Remember, if this is an acidic solution, that means that the hydrogen ion concentration is greater than the hydroxide ion concentration. Okay. I'll see you on the next video podcast.